Okay. So hello everyone. Welcome to this week's discussion. So today we are gonna discuss lecture 11. So tracer tracking modules and a 3D Lagrangian particle tracking program. Before the class, I have received two questions, and I will first show them here. And after these two questions, if you have more questions, please read them up. So let me first share my screen. And the first question is from Minwoo Park. Minwoo, would you please say it in detail?
Okay. I created a 1D channel with a maximum depth gradient of 15 degrees and set up vertical gradients for temperature and salinity using the linear time TS type. And then I set all external parsing variables to zero in both the name list and source code, except for the baroclinic pressure gradient calculation variables. And next, please. Uh, uh, and I added the discontinuous steps at the center of the 1D channel to create three cases. Case 0 is the reference case with no depth modification, and case 1 has 9 central nodes modified to 1000 meter depth to create a gentle seamount, and case 2 has only one central node modified to 1000 meter depth to create a sharp seamount. And next, please. Uh, from the model simulation result, no motion occurred in case 0 and case 1, but motion did occur in case 2, uh, and the case 2 blew up. I'm curious about what caused model instability due to discontinuous steps. Could this be related to sigma coordinate? This is my
No,
question. Thank
no,
you.
no. Yeah, that's crucial. Let me just you. I think you have to be very
Yeah.
careful in doing experiments. Okay, there's a lot of that's not it's not a sigma error. Okay, yeah,
Yeah. Next question from Jim Young Seal.
yeah.
Yeah, I study for this lecture, so Lagrangian particle models show and follow this equation. So I wonder that some simple questions. So this equation shows only position of the particles, effect only velocity, but I wonder that if some cases, for example, with FVCOM in sediment modules, uh, some sediment suspended and their sedimented concentration, I think that will affect for particles, but this equation not consider that. So I wonder that how we can consider that the other factors in velocity is that my question.
Mm-hmm. Mm-hmm.
Yeah. So these are the two questions that I have received. So is there any other question? Uh, if you have any other questions, please feel free to read them out today, and then Dr. Chen and I will answer them together. No? Okay, so let's start from the first one.
Yeah, first one, I think I can address the question. So go back your three cases. So go back three cases. Okay. Your case one, your no depth adjustment. What it mean for no depth adjustment? So second one, you see the case one depth changes uh, of ignite here. Okay, depth change. Okay. Why? I don't understand what is the depth adjustment. What does it mean for you? Okay, I just need that one.
So
Case
it,
two.
It just means that there is no seam mount
Oh,
in
see,
the
no seam mount. Okay, but it's
yeah.
still okay, but you still, had a topography, right?
Mhm.
So then you had case three, you said that you had a depth changes with one central sear, one central sear. Okay. Okay, now what happened, so you go to run the model, go back to the second slide. No, go to the second slide. I want to see what he set up. So then you go to okay, you go to the second slide, so you set the value, you put everything's 0, and viscosity is 0, okay. Yeah, go, yeah. So then, just look at the table, look at the table, look at the
There you
table.
go. Okay.
Yeah, mixing coefficient, you get everything's 0, okay. So you ask the bottom rest 0, most, heat budget is 0. So then you get a boundary, coefficient 0, everything 0, okay. So, but the barochromic pressure grading, not 0. No, barochromic pressure grading, yeah, you can get barochromic pressure, you definitely get barochromic, you need to calculate it, right? So you said you idealize the experiments to conduct a 1D channel, okay, 1D channel. So that's if the 1D channel, be really careful how you set the channel, because you do I think that you do the 1D, this should be 3D, right? Are you really set for 1D, 2D, 1D channel? So if you set a 1D channel, if you only do the 1D cases, you have to be very careful. You have to make sure because you have to make sure all cross self that's uniform, not changes. Like we do,
Yeah,
yeah,
it is a 3D
yeah,
grid, but
3D case is channel case.
yeah,
You
he
took,
he
yeah,
mentioned he
yeah.
tried to mention 1D problem.
Okay, yeah, 1D, it's not a 1D problem right now. If it's 3D cases, because
Okay.
you put a C mount in the region of the line there. So, but then you have it so narrow. Okay, so no test question one. You do see if a slope region, you don't have a forcing everything there. So you don't have a more topography. You get a 0 C. This means temperature changes. Nothing had changes, right? That's correct. That's the answer you get, right? So the second one, you said, okay, you put a C mount there. You put a C mount there. Where is the C mount? Where is the C mount? How you put it in? I'll put it here, okay. You put it here as a C mount, okay. That's a rectangle, but that's really, the C mount. That's the C mount was put it here. You was use like a square C mount.
Yes,
Yeah,
I
that's
said
yeah,
yeah.
you put a square, the C mount over there. So then that's really interesting. You put a C mount there. But however, you're the coding, the second one, you said put a C mount there. So you put every forcing is 0. The second case.
Yes, every person is 0
Yeah,
in
every forcing 0, you put a stratification and a C mount there. So you do case 2, you find a higher velocity come out. Then you get the pressure.
oh, mm,
Yeah, I was I was I don't know how you set up. That's the cases, okay? You put a C mount there. I know you put a C mount there, but in the case two, you said that you had topography change was in nice there, but come out, you don't have any flexion, any forcing, but you do find this is gray, right? It's gray, Mount gray.
yes, this
Model
model.
does want to go. What sort of is the result? So then you find second one case, if no forcing, no flashing, no stratification, no temperature, no change with time. Only for case 3, 0 case. You miss the case 2, okay, just like a case 3, okay, right? Case 3. So now you put what do you put case 3? Let me go back.
Every case, there's no forcing. The initial field
of temperature is given in that pattern. So the heavy water under the bottom and lighter water on top.
But what is different for 2 and 3?
Only the topography.
Or topography, only topography, okay.
Only depth.
Okay, topography, yeah. But then
Only
you see,
depth.
yeah, I think the problem right now, your model, if you make this kind of shear topography, if you look at my paper, if you put like a shear topography, you need to have a very high resolution. You're not able to run the model with this same resolution, you have one great side, right? Change the topography certainly. So that's model not a, that's why I said if you want to reduce the error, you have to make a high resolution around the, if it's about steep bottom topography, right? So that's why but now you put a high cost resolution, topography certainly changes. Certainly one change like steep, like a straight wall, most like this, right? So then then you can cause this probably lead to sigma error, but you see this model even unstable. I believe you're not unstable because your resolution so coarse. Okay. No, I don't think it's a good example to test that. No, that's why we will say clearly in the user manual said if you put a steep topography, you have to increase model resolution. Okay, so then you can reduce like a sigma error, but this is not only sigma error; it's a whole model unstable. You find whole model unstable because you put only there. You put forcing. You put everything there. Like a very steep topography, right? So then the question come out. I just ask you to check. That you look at you after run the model, what temperature look like?
The true solution should be nothing change.
No, the third solution, third one.
So the next slide.
You go back to the next slide, Struga.
Well,
Yeah.
so
You
I mean the first.
you don't quit. Just down here, just down here.
So
Yeah, just keep not moving the movie. Okay, just give it time. Okay, just fix it. Time. Okay.
Sorry, doctor, I cannot stop it.
Yeah. But
It's a gift.
you better not only show the movie. This is because this is second movie. We sea surface elevation. We're not able to see anything. You see what I mean? Because you're so narrow. Okay, so narrow. So your topography put it in the whole cross channel or just put a center. Okay, if you put a center there, so you're so narrow, your resolution is so coarse. So that's why your arrow, your horizontal temperature you put it in there, right? So that's can I don't know what the model can wrong. Okay, I know. So you can test the one case. You can test the one case. You have to put like a 2D model exactly, but you don't want the side boundary affect that. You to the model that. Then you put a topography, in their line, so you can see how the sigma error how to changes. Okay, but you only have one shear, change the depth, from 1 meter to 300 meter, 3,000 meter.
Yeah, 3,000 meter.
One grade, 3,000 meter. How you run a model? You're not able to do that. Okay. No matter what the model you want to put in there, no matter it's structured, unstructured model, it's not running.
But Professor Chen, actually, yeah, I totally agree with you. And so Minu push the model as far as possible. And for this case, Minu used just one single CPU, so there's no MPI.
No, that's no CPU issue.
Okay.
That's another issue. We talk about CPU issues, but multi-exchange, that's a different issue. But this one is
Yes.
only one single CPU, but your topography is so stable. Your model resolution, your delta T you cause like an arrow, the arrow can develop very quickly, but you're so steep. Right?
Yeah, but
That's not a parallel rounding issue, okay?
yeah, but
Yeah.
still, I have still some question because in this case, there's no forcing.
Yeah.
So there should be no, how can I say?
Because your model is not satisfied, stability criteria,
Mm-hmm.
right? So you
Mm-hmm.
have any kind of perturbation into the model become unstable.
So then the next question is, then how come in the second case, in other words, the name is case 01, how can that case is stable?
Yeah,
Because in the
no,
second panel,
this one, because even this one you calculate because you have no pressure gradient calculated, okay? But you put the pressure gradient on there. If you look at my paper, 1998, 1995, appendix, I read it clearly how this no forcing, no condition, had only topography. For sigma transformation, they can get a perturbation come out. I had an equation show you what a perturbation look like. Okay? So then the equation come out, if you have any kind of sigma perturbation for this case, you can intensify very quickly bigger. When it quickly bigger, then you don't satisfy, it's the stability criteria. They can develop very quickly. Okay, so what we're talking about sigma arrow is talking about, okay, we're talking about a sigma, talking about just tell you said, you satisfy the computation stability. You had no instability problem, but this way you still had a sigma arrow. But how that's kind of sigma arrow is to look like. But the case you do this is completely unstable. Okay, you're not able to set the grade no, you have so narrow 3D, you put a square grade inside a square, but both sides of the wall. If you any perturbation, they come to the wall, they probably in the way there. So then it becomes unstable. Okay, this experiment is not good experiments to be honest. Okay, if you really want to look at sigma arrow, I suggest you rerun a case we did. Okay, you see, have you look my paper?
Yeah, about the C mount, the circle.
Not a sea mount. I look about a lake boundary, the cylinder lake. Okay, so then you can put a slope on the coast region. You don't put a forcing on there, they can cause the sigma arrow. Right? So in the case this one here, we put it there. We found that if you put a link trap with no forcing, no flexion, they don't show the motion for all time, right? However, when you put the bottom flexion a little bit, so you cause the motion, right? The bottom boundary layer. But this bottom boundary circulation come out, it's not true circulation, not result of bottom boundary layer because they get a sigma arrow. But then you reduce the resolution, you can reduce the arrow, you can come on the bottom boundary layer. Okay, so you can can you open my paper?
Yeah.
Yeah, I want to show you. I want to show you. So if you're interested, you can test that one to see how learn how the sigma arrow is. Okay, that's the benchmark testing. We everyone do that way. Okay, because the way you set up, you can cause a lot of other problem, right? The boundary issue, all issue. But then the question, I think that's a 2007, 2008, 2007. Yeah. Not one, this one. No, it's 2007 again. Just I had a comparison. We also had a compare with wrongs, the structural gray model. And before we had a comparison, no. Let me see that.
This one?
Yeah, this one. Yeah. No, not this one. Yeah. Why we repeat? Hey, this one, yeah, this one. This one, yeah. The first ones I did the comparison, the simple arrow, second one compared with the structural gray model. Okay. You look about this one, you go down. You go down here. Go down. Yeah, you see the case we did? not this case. Go down, sigma error case. Good. Case we did. No, go down. No, not this one. Not this one. Not this one. Not this one. Go down. Go to end. No, here. You see? No, go up. Go up. You look here. You look here, this picture. So you do the cylinder, you just get a section here. The four things that you want to see, that the circulation is symmetric or not. Right? But then you see if I don't put any forcing on there, they don't have any circulation come out. Now I put the bottom fraction, small one. I put a 10 to minus 4. Right? That means because the bottom fraction, they can mix a fraction, they can produce the motion. Because at fraction, you have to have a flux equal to 0 at the bottom. Right? Your temperature had to bend. Right? Your temperature had to bend. Because in your case too, but if you don't put everything on 0, is no problem. But when you apply the boundary condition, partial T, partial Z equal to 0. Right? In the bottom. So that means your temperature had to bend. You understand? You see here, if you had a slope, something like this, okay, you put a temperature like this. So then you assume temperature bottom in the bottom, like a wrong everybody model show this equal to 0. That's your model setup, right? If you don't, then what happened? Your temperature had to bend. Right? Because flux equal to 0, that means your flux sometimes look for this condition, the temperature bend like this. The foot bottom there. Then after the temperature bend, you cause a pressure gradient. This cause the motion come out. Okay? If you don't have any forcing there, but if you apply the bottom boundary condition like this, they cause the motion. That's what I mentioned here. But this motion is true or not? It's definitely true. It's called a thermal bottom boundary layer. But the question is, when you have slope, you get a sigma transformation. This kind of motion probably contain the sigma error. So this way, you see here, that's a comparison. You see here, if I make a resolution 4.5 kilometer, I can produce the motion like this. Both Pong and FVCOM, the structure grid model, they both have a circulation like this, but this circulation is not true circulation. It's partially true, partially is a sigma error. Then you go downstairs, another one. Go to 20. This one, you see this one. So when you reduce the resolution, resolution becomes a little bit high. That's happened for 10 days. About 5 days or 10 days. You still get the circulation like this way, even symmetrically, but you don't know the circulation correct now. Right? So go down next one. So then that's what happened. When you make a resolution really high, you do see the thermal boundary layer come out. It's a very narrow circulation with the code like this way. That's a true circulation. Right? But the one you showed before, that's mostly sigma error. Okay? You understand, right? You see, even Pong can resolve the bottom boundary circulation too. But however, he's probably a little bit wide, not symmetrical. But then FVCOM can be symmetric. You see here? Okay? So that's the reason. So you find this reason here. You find that that means if you consider it this way, your sigma error should be smaller. Right? That's why if you reduce the resolution, make the resolution very high, so your sigma error can decrease. Okay? You see me? right? I didn't put any forcing. I just put a background mixing, just like I put a flux equal to 0 at the
And
bottom.
but in this case, you didn't turn off the Coriolis.
No, we turn on Coriolis first.
So I mean, in Minu's case, he turned off Coriolis too.
No, I know, if you turn on the Coriolis, then you get a big trouble too. Right? Coriolis can make a circulation around the cycle, but you want, just go to this way.
Yeah.
Then you go a little bit. That's why the case, no, because you want to see if you turn on Coriolis, you can see does it geo traffic or not.
So he
Yeah.
doesn't want.
Yeah, but he didn't want this one. But then you really wanna, you don't really can see what a sigma error is. No, I think it will happen. Go back and read my 1995 paper. I had to tell you what sigma error physical mean. Now is the people really use a topographic coordinate model to say, oh, that's a sigma error. That's a sigma error, right? In anything topography come out, this sigma error. No, it's not all sigma error. You need to identify what sigma error really defined is. Okay, you cannot see in any bottom circulation is a sigma error, but you do have a thermal boundary layer. Okay, you look at thermal boundary layer circulation, you see here, right? So I think the part of upwelling, you also can see the upwelling here. You see here, so what is it upwelling? This upwelling is a thermal boundary layer. If you go to look at 1974, like 1974, I think Carl Walsh, MIT professor Carl Walsh, that's my teacher. Okay, Carl Walsh, 1974. Okay, when I was a graduate student, I was working with the Carl Walsh about internal wave. So he developed the first paper about the bottom boundary thermal boundary layer theory. Use turbulence theory. Then he had all to see how if you had a stratification, how the stratification is. Then you see how the thermal boundary W should be. Right. So this way you can see if you can resolve the thermal boundary layer, that means that your sigma error should be very, very small, ignored. But only happen, go back. Go back. Only happen if your resolution cause, that's error. If you cannot resolve the thermal boundary layer, that's all sigma error. Okay, that's why you have to make a resolution high until you reach to thermal boundary layer. But then the question come out, a lot of people don't want to use very high resolution on the slope region, right? Well, of course, then you have to pay for sigma error. But if you that's the reason if you look at our northeast Georgia bank, our northeast forecast system, you see on the slope region we have a very high resolution. Right? This reason we just want to resolve the bottom boundary layer. Okay. So if you look at so Dr. Lee, can you go find the 1995 paper?
Yeah.
I want to show you the theory, okay? Now you understand? Okay. (1995). I had a JPO paper, Yeah, this just this paper. Yeah, symmetric band. Yeah, this paper, yeah. You look at for the appendix. So you can ask me. You can see that's a sigma error because it's a bank, like an island, right? You can sigma error. You see that's the sigma arrow I defined. What does sigma arrow mean? Okay. You see what I mean? Here is you look about a whole equation, what I mean. Sigma arrow, go down, go down, go down. I just want to show the, then you want to see you want a calculation the geotrough velocity. That's the arrow, right? So you are the criterion, you have to be topography, had to satisfy as an equation, go back to the equation. Here, that's the most of the sigma arrow come from, like equation like this one. No, go back, go back. Yeah, go down, go down here, go down. I want to show the equation. Yeah, go down. Yeah, you look here. Okay, you see the sigma arrow. That's the velocity. Over here, you can see the velocity. You can estimate what the larger sigma arrow velocity is. Go down. No, you see here. No, when you topography the slope is great larger than this one. This turn can be enclosed like a sigma arrow. This is an arrow depending on the slope, how deep slope is, how about the resolution is. Okay. So if a slope very steep, arrow can be bigger. If you have a resolution is bigger, your resolution cost, you can cause a bigger arrow. You can use the equation to identify, but then the question comes out, I use the Clark-Wonch theory. You see here? Yeah, okay, good. I think, Clark-Wonch, 1970, I'm sorry, wrong. 1970, he will talk about the boundary layer, diffusion layer, thermal boundary layer. That's the diffusion layer thickness. Okay, depending on the stratification, depending on this. So you can make an estimate. Okay, so you can know how the thermal boundary layer should be look like. How the order should be look. If you get the stratification, temperature put in there, temperature, the additive viscosity put in there, you can expect what the thermal boundary should be look like in the bottom. Right? So if you don't reach this one, that's a sigma arrow. If you can reach the condition, you don't need to worry sigma arrow. That's a true solution. Okay. You see here, that's I estimate go down to a little more. Yeah, you see here. That's what the equation I define. Okay. Park, I was suggested to go to read this paper. Okay. Right. Understand what is a sigma arrow. What people talk a sigma arrow. You don't want to follow everybody say. You want to see what you critical thinking. So what it should physically what a sigma arrow is. Right. So the problem is most of the problem with sigma arrow is the resolution issue. You can reduce, you can increase resolution, you can solve a sigma arrow, definitely. But however, a lot of people don't want to pay for that. Right? Now, if you have a better, if like we do the model, I can show you the model results, but no, I can show you some model results, very high resolution model, right? So we can do the very cylinder, we can do it very quick. So recent new coding, you get a circulation come out, very stable, right? But then we did not certify the converging solution. Converging solution, like I show you the test there, I make resolution high and high. I do the thermal boundary come out. That's the converging solution, right? The one I showed you before is not a converging. That's a numerical solution, right? So you have to reach the true solution. So you need to do the converging study. Okay.
So, Professor Chen, wow, yeah, we should and Park also should look at this paper very carefully. The boundary condition for temperature, as you said, dT, dZ need to be 0.
Yeah.
So all this the thinking or problem really comes out from that condition?
No. I mean, so even you don't have a forcing, if you put the boundary condition on, you temperature has to bend.
Right. So
Right?
that boundary condition, we cannot really change that boundary condition, right?
You don't see the boundary condition, but you specify in the model.
Yeah. So that is typical specification of the temperature.
Yeah. But then the problem, if you like second two case, you have a topography, you specify 0, you put everything 0, okay?
Yes.
Right? So you don't have this kind of strange topography. Even you put this boundary condition, it's not a function where, okay? Because so now, but when you have a steep topography, they bend so too much.
Right.
Okay. So then they come out, but then your case, when you come out, your case resolution so-called, you're not stable. Right? You see, that's the reason you see what happen. You don't have a cross forceps. They're not able to turn around.
Yes.
The arrow cannot traffic it along the topography. They have the propagation out. That's why you get every place all the arrow. Okay. I think I suggest to go back and read my paper. Okay.
Yes. We should.
When you do the additional exercise, read my paper first. Okay.
Okay.
Okay. Good.
Good.
Okay. No, I think Dr. Lee can send 2 papers for you to read. Okay.
Yeah.
Okay. If ever other students like the paper, like to read paper, you can read too. Okay. Today I give it to Jun Yang, my ecosystem book.
Oh.
Okay. We'll talk about stability, talk a lot of things. But however, this book is written by Chinese. That's terrible. So then Jun Yang said he can transfer AI transfer in Korea very easily.
Yeah.
So I hope Jun Yang can transfer in the Korea words or like language. Put online people can. I don't care for copyright. Okay. So you can read. Okay. You can understand how ecosystem model, how you define ecosystem model, how you state instability, how state the solution, how to look like, why you need to do that. In the book is rather very clearly.
Okay. Good. Okay. Wonderful.
Okay. Yeah. So you can see that. Yeah, you can see that. Okay. We go to the second question. The second question is really interesting. Okay. First things, Lagrange particle tracking only consider about the particle. Okay, it's not consider any kind of concentration like a sediment or others. They only driving by flow, right? But if you have a sediment there, the flow can changes. For example, you had a sediment band in the bottom. The fraction becomes bigger, then flow can be slowed down. Then the particle can be affected. But they change it, sediment, suspension, everything change the flow, right? Now we change the flow. Then this flow will change the particle, right? But however, this kind of particle tracking, particle tracking is a good study, but particle tracking has a problem. Because particle is like a neutral particle. They only consider drifting by the floor, by current, but they don't have a representative for mixing. Right? For example, your water stay here, you track the water from here to by the current. But however, sometimes if you look at the red ocean, the water can be mixed together. But then this one did not resolve that. So we try to resolve the mixing in the particle. We put like a random walk mixing. Just we put like a particle tracker. If you look at our Lagrange coding, we had a random walk option there. Right? So that means every time we track the time, for example, 2 minutes, during the 2 minutes, we let the random walk every second. Right? A random walk. Then out of random add in the position for particle. Okay? But the good things, vertical random walk, people understand the word well. A lot of people use random walk. But I want to tell you the criterion how you use a random walk. Make sure you don't have a particle converging, diverging. If you put a two particle, if you find your Lagrange particle tracking, you get a two particle arrive the same location. That means your particle trajectory is fair. Okay? The reason because that means, for example, you put one parcel into the water without mixing. The parcel can change its shape, right? Because you assume ocean is incompressed ocean, right? So the parcel can change the shape, right? If it becomes longer, then become narrow, right? Right? They become high, the shape can change it. But however, the volume cannot change it. Right? The shape changes, they can because you was incompressible. But if you compressor, you can press on the very small bit bigger, right? It's very bigger, but in compressor, that means you ship, can change, but the volume never changes. But in this way, so if the particle, you have a two particle, you cannot arrive at the same location at the same time. This means you're not in compressor, not continue anymore. Right? So the problem is a lot of random walk putting in there. They was put a random walk or crystal location. Sometimes not a good method. They can put your all particle accumulated at one point. I told you when I was younger scientist time, I do the particle tracking and the tide mixing from. I found all the particle from up, deep ocean, then avoided to the front zone. So that's all accumulation there. All accumulation at one point. I'm so excited. Okay. So then I found I run about MPZ model. I do find I had a phytoplankton accumulation there. Right? So I so excited. I go to MIT. I talk to my professor Graham Floor. Graham Floor is a very smart person. I think most smart person in the ocean science. Okay. Graham said, "Chen, you're wrong." I said, "Why am I wrong?" Why? I fly from Georgia, go back to MIT, talking to him in the office. He was telling me, he said, "Chen, you're wrong." He said, "No, yeah, your results are perfect. Really exactly same as your MPCC model. But I try to use this product trajectory explain how the nutrient come from." But he said the good. They do see from the deep ocean, but however, your accumulation is impossible in the fluid mechanics. Right? Because it's against the mechanical law, right?
Yeah.
So then he and I was talking on the blackboard most about half a day. Do the whole mathematics. Finally, I be convinced. I say I'm wrong. Okay. Right? I tell you, that's why you be careful if you run a particle trajectory. If two trajectory, two particles locate, you put many, right? They can accumulate it together. You get into trouble. Okay. So for a lot of random walk theory, they put the Lagrange tracking. You have to test the first. If you find this kind of Lagrange, random walk can make the particle all converging together, that's the random walk is not correct. Okay, that's why you look at the paper. Some people say I use this random walk. I use this random walk theory. Don't just adopt immediately. Do testing. Right? That's what a FVCOM random walk has been tested many times. Okay. Now, after I make a mistake, so then also I think Kennedy size the other people I couldn't remember him there. He introduced another random walk theory, but also pretty good. Okay, but you have to test it. But the issue is come out not vertical random walk, because the vertical random walk we know the vertical additive viscosity, we know the water, we know how large what the profile, because people not do the bottom boundary theory. Key issue come from horizontal diffusion. Horizontal random walk is really critical issue for ocean modeling, but you don't really know what the horizontal diffusion coefficient is, right? In the numerical model, most of the horizontal diffusion we put Smolensky said, okay, resolution becomes higher and higher, the horizontal diffusion becomes smaller for physical side, okay? But then you look about a coast region, you look about a global ocean model. The global ocean model, right? He put the horizontal diffusion 10 order to 6, 10 power of 6. Huge meters squared per second. But then you look at the coast region, you go to the coast region, you find nearby the tide mixing front, like a short big front. Then most of the horizontal additive you do dye experiments, you imagine, most like a 10 meters square or 20 meters square per second. Because horizontal diffusion has changed significantly. You really don't know how you primarily random walk in the horizontally. If you put it larger, it diffuses really quickly. If you put it small, right, it shows nothing. You don't really know what it is one. I did experiments. Okay, we put like a more than, I get a picture. I'm not sure I can find. Okay, probably I can find. We put a more than 10 drifters at the same time. Okay, in the coast region, then we find a drifter diverse, diffused, go out. So then we use the FVCOM model to trace the particle trace, see how we follow that. We follow the main pattern, but FVCOM showed less diffusion. Right? So then we try to put a horizontal random walk into the system, see how you can diffuse. So that's why because the horizontal diffusion changes with the time, so it's really hard to change it with a random walk during the time horizontally. That's why we didn't get a really good match. I'm not sure I can find it. If I find it, I can show you. That's how the particle trajectory. But to your answer, make your long answer to short. So sediment definition can affect the particle, but but if you really want to see, how this thing is changing, because sediment, the coupling just sediment change, they change the flow, they change the mixing. This way thing can be affected particle trajectory, but the particle trajectory coding don't have a mechanism show how the sediment directly changes. Okay, right? But I can find I'm not sure I can find a paper. I do mention that paper because I do the Koda experiments. Okay, do the ocean, So I do have a comparison for the drifter study. I want to show you if I can. I was go to talk, okay. Let me see. I had a conference. I think it's 3. Yeah, I think it's this one here. Okay, let me find it. If I can find it, I'll show you. Okay. Okay. No, it's not this one. Okay, PowerPoint. Yeah, this one here. Okay, I want to show you the one slice. No. Okay. I don't want to show. Yeah, you see here. I want to show the one slice to you. You see, okay, you see that slice? Do you see the slice? So this red one is a drifter. Blue one is a FVCOM model result. So you look careful. You look at this one here. You see the red one is a drifter. You see the drifter. You see a lot of some couple drifter go this way, some couple go that way. But you see the FVCOM so diverse. But this group is pretty good, right? But this group, you see, they are very narrow, but FVCOM should be diverse. Right? That's trajectory. That means that's a question come out, so how you can that means your model diffusion, Hurrian diffusion coefficient is a little bit bigger. You make the currents so diffuse. Okay, you see here that red is a true drifter. Red one, no, blue one is the model. Then you see the model trajectory is so diverse. You see here. No, model show like this way, right? But the really trajectory look like a group go this way. So in this way, you can testing your model Hurrian diffusion. There is overestimate. Okay. So you can do a lot of experiments. Okay, this one, this is quota experiments. Okay, I just showed you. I just showed you an example. Okay. Do I answer your question? But I told you the one thing. I like that Dr. Lee has recently found our tracer coding online is not correct. And the coding, so there, I think Dr. Lee already made correction. We also develop offline tracer coding. So we can, if some people want to use, we can share with you the cloud. You can use FVCOM, you can use the tracer pool there, see how it's moving. You can check out the warden, so conservative or non-conservative. So we recently correct the online error. We also make it offline is available. You can not a particle trajectory, it's a tracer. Okay, if people interested in testing, so we can in the class we can provide a code. We just got down for last week.
I mean, if it's possible, then we'd like to apply that module for the Han estuary. Especially nowadays, we have a marine debris problem. So maybe sometime, if possible, then I will introduce the
degree problem. Probably use like longitudinal particle trajectory better than the tracer. To be honest, okay. Because debris look like debris is like a materials like a puzzle, right? So that's why debris is not a mixing, not cause of mixing with them together. They're not changing the debris. That's why you can use the particle trajectory pretty job. You also can use tracer. Tracer is a concentration. Now Dr. Lee probably a couple minutes show what the code what it is.
Yeah. So I just introduced it briefly. So this time we first fix up the source condition for the die for the die source point, and before we set it manually at one point with a fixed value. But now we consider both the discharge volume and the discharge die concentration. So this is the first part. And the other part is about the offline die program. So now we have, before we only have the Lagrangian particle tracking offline model, but now we also have the offline die model. So for this die model, we can first run our physics model to get the horizontal velocity and also the coefficient like kh, and then you can use the existing physics field to run the offline die program. So in this way, you can save lots of your time. And also in the offline die program, we did the we use a continuity equation to recalculate the vertical velocity as well as the predicted surface elevation at the time n+1. So in this way, we can get a more correct result.
Picture, but probably time too short. We're not able to show a picture. We're definitely able to show the coding. You can do that. Okay.
Yeah. So and also this time we first did the test using the idealized case, and within that case we know what the true solution is. So by comparing with the analytic solution, we know that now the coding runs right.
Okay.
Wonderful.
Yeah. So any other question? Parks are good. You start the sigma arrow. It's interesting. Okay. Yeah. Keep hard working. Okay.
Is there any other question? So after today's discussion, I will upload the video on the YouTube. So if you're interested, please feel free to review. And I will also send out the 2 papers that Dr. Chen mentioned. One is in 2006, the other is in 1995. So please check your email. And the next week we'll discuss a lecture about the data simulation. So if you have any question, please send me before the course so that I have enough time to summarize them and save more time for the discussion.
One thing that I like to mention, I talked to Dr. Xu today. He already finished modifying the coding for vertical hybrid coordinate. But now he checked the step by step because he moved to so large a coding here to check step. So he want to make sure traditional topological coordinate model still can run without an iteration. So then you go back to new. So we hopefully in the May we can have a new coding tested.
Okay. Well, that's great news.
New coding tested. So then you can much efficiency, you don't need to start the sigma arrow anymore.
Wonderful.
People, when you look, some people kidding you say, "Oh, we make like any model resolution, we make like any quality triangle, we can run the model stable." But you can run the model stable doesn't mean you can write the physics, right? Your model stable, like some people use some model they run, they kind of currents are opposite. But they say the model stable look like pretty good, but they don't really know from complete observation is the opposite. That's why. So sometimes the sigma arrow can warning you all time, right? Let you know some stranger you think about that's probably come from this one, right? But if models are so stable, everything run beautifully, then you say, oh, that's everything you trust, everything's true. Like when I was doing the Lagrange tracking, I get a accumulation. I think I get a new funding. I'm so excited. I fly to the MIT to talk to my advisor. My advisor said, "You're stupid." I like my advisor was an older advisor in MIT. If I stupid, they tell me, "Chen, you stupid." Okay. So sometimes I told my advisor, "You're stupid," right? But we are very friendly to talk each other. But now it's all people old. A lot of people already passed away. That's made me very upset. Okay. Yeah. Anyway, good.
Yeah, so let's end it up here today. So thank you so much for joining this discussion and see you next week.
See you next week.